Namaste and Jorle. Uh, Today I'm here with another new interesting video, and it is related to thermodynamic potentials, right? We are going to deal with important thermodynamic potentials, and then how do we get a Maxwell identity? Because these are the important parameters we need to know in order to have a speciality in statistical physics or thermodynamic physics, right? So without any delay, let's go into the thermodynamics part. And what are the important thermodynamic potentials? And then I'll conclude my this video with the introduction of Maxwell identity, or how can we get the Maxwell identity. Yeah, I'll tell you the easy steps, right? So let's go into the our content of today's. So without any delay, right? Let me let me start with this one. Now, if you look at this one, now if we look at this one, right? You can see over here. This is first law of thermodynamics. You can see in a circular pattern in red, in black color, right? This is the first equation of thermodynamics, and it says that the amount of heat supplied is useful in the changing in internal energy of the system and work done on the system, right? Work done on the system or work done by the system. So if this is this as a system, this is a closed system. Let's consider this as a closed system in which the number of particles is not changing, in which the number of particles that n is not changing and is not changing. Then the amount of heat supplied to the system. So let me use different color, right? The screen on. So the amount of heat supplied, that is dq, to the system is useful or utilized in changing the internal energy of the system and the work done by the system. So with the increasement in the heat energy of the system may expand to somewhere else, like that. That is the external work done by the system, right? Present in this system, present in this closed system, right? So we can take example of this cylinder with piston air also. So this is the cylinder with a movable piston with no friction present at all. So there is the working substance over inside this container, inside this cylinder, and if I supply certain amount of heat, that is dq, then this dq is utilized in increasing the internal energy of the system, which is the summation of potential energy of the molecules and the kinetic energy or vibration or motional energy of these molecules, plus external work done that the system, that this working substance does on this piston, right? So this movable piston, due to the presence of heat supplied from the external source, it can move towards external outside, or it goes outside with the change in certain volume. This one is the change in the certain volume, right? So this is the change in the volume, and this has been done in constant pressure. At constant pressure, that's why the this is the heat supplied is equal to the change in internal energy plus amount of work done by the working substance. So now further we can write dw, that is work done by the working substance inside the cylinder, can be written as p times dv. And all of you know we can write this one, right? So simply I have this equation, dq is equal to du plus pdv. Or I can have this equation, if I write du, then change in internal energy is equal to dq heat supplied minus p times dv, right? Now we are considering that the number of molecules is not changing because it is a closed system. None of the molecules can go inside, nor it can go outside from this system, right? That's why number is constant. Further, at the end of this uh, at the end of this thermodynamic potential, I will let you know how to deal with the change in the number of molecules as well. So now, and this is from the second law of thermodynamics, right? So this is from second law of thermodynamics. This is the entropy in terms of the change in heat energy divided by time taken. So change in entropy of any system is equal to the change in heat energy divided by at constant temperature. So dq can be written in terms of ds and time, dt. Sorry, ds times t. And let's substitute du, that is the same quantity du. The change in internal energy is equal to t dq is can be written as t ds. This is from second law of thermodynamics, and pwv remains as it is. So overall, we have this equation, which is the combination of both first law of thermodynamics and second law of thermodynamics, right? So this is the differential form of internal energy in terms of entropy and in terms of volume, with parameters temperature and pressure, right? So this is one of the important thermodynamic potential, and that is written here. This is the internal energy. So internal energy is one of the thermodynamic potential. And if you look at the uh, uh, coordinates related to internal energy, or the variables related to the internal energy, that is the function of entropy, volume, and right now we are not taking the molecules as changing parameter. That's why it is the function of entropy and volume right over here, and which can be seen clearly from this differential equation as well. This differential equation, that change in internal energy does depend on the entropy, does depend on the volume, right? So this is the function of entropy and volume. It is not the function of temperature and pressure. These are the constant parameters right over here, right? So this is the only function of entropy and volume. Now let's go into the number of particles. If there is change in the number as well, so what could be the relation? So the equation remains as it is. The terms the terms relationship remains as it is. What we have to just introduce, instead of these two parameters or two terms, we have to introduce with the number parameters, and that is given by 2 mu times dn, right? So if there is change in number of particles, if in this system I can allow number of particles to go in or to go out, then the internal energy does depend on the change in number of particles as well. So the internal energy is the function of entropy, volume, and finally number of particles inside the container as well. And this mu is none other than the chemical potential. This mu is none other than the chemical potential. This is chemical potential, and it is similar or equivalent to what we studied in electricity part, that is chemical potential is equivalent to electrical potential or gravitational potential. So this potential is related to the particles, right? So this is and this is similar to, or analogically we can treat this chemical potential to electrical potential, that is related to the potential with respect to charge, and gravitational potential, that is related with the potential with the mass. So this is equivalent to the those who can analogically relate chemical potential with the others. So if there is change in number of particles, then there will be the change in internal energy as well, and this is related by the mu times delta n dn, right? So this is the overall equation for internal energy, and this is the differential equation for internal energy, and it can be clearly shown here that it is the function of entropy, volume, and number of particles. So internal energy is the function of entropy, volume, and number of particles. And let's go into the second thermodynamic particles, right? And let's go into the second thermodynamic particles. And second thermodynamic particles is enthalpy, or enthalpy, and enthalpy is the heat content of the system, and it is defined as it is the summation of internal energy and pressure times volume. So internal enthalpy is numerically equal to internal energy plus pressure times volume. This is the definition of enthalpy, right? And it is the heat content of the system. So again, it is the function of entropy, pressure, and number of particles. Now look at the just difference between the internal energy and enthalpy. You can because this is a science, right? And you have to think about uh, technically. If you think technically, or if you study technically, then it would be easy. Otherwise, all the things you have to study for each part and each bit of information you have to read, right? So if you think technically, then you can relate one parameters with the other parameters. That's why I'm just giving you my technique of studying in science, right? So now the only difference between them is the presence of P and P. In this case, internal energy. In the internal energy, it is the function of entropy, volume, and number of particles. But in case of enthalpy, it is again the function of entropy and number of particles. But instead of volume, it is the function of pressure. So the only the change between them is the volume and pressure. Internal energy is the function of Spn, and enthalpy it is the function of Spn, and it is mathematically defined as the summation of internal energy and pressure and volume, right? So now similarly we should know why is this the function of entropy, pressure, and the number of particles. Now if you write the differential form of this one enthalpy, then you will be clearly known that this is the function of entropy, pressure and number of particles, not the function of volume, right? Similarly, as we did in our internal energy case. Now let's write differential form of enthalpy. Then after that you will be clearly known. So differential form of ds will be equal to in differential form of du internal energy plus and differential form of pressure times volume. So from product rule, this is the like this, right? Differential form of pressure and volume, pressure and volume. Now differential form of pressure is from product rule P times dV plus V times dV, right? So this is going to equal to, now let's write du in terms of these parameters, as we already know it. So it is T ds minus P dV plus, and this is due to the differential form of dPV, right? And if you want to write, or if you do not take numbers as a constant parameters, then you can write this one finally mu with dN, right? So now if you simplify this expression, this pdv and plus pdv and minus pdv is going to cancel with each other. So this is pdv and this is minus pdv going to cancel each other, and final expression will be like this: tds plus pdp, right? And mu times now dn. Now ds the differential form of h, that is enthalpy, is the is related to tds plus bdv plus mu dn, and it is clearly stating us that it is the function of entropy, pressure, and number of particles present inside the system, present in the system, right? Not the function of volume, as we saw in our internal energies. So in order to know the functional variables present in the thermodynamic potential, you have the better way to deal with each other is to write the differential form and get the differential parameters which are changing, right? Differential coefficient which differential functions are have differential forms, right? Then we can clearly know the different functions of certain thermodynamic potential with respect to certain thermodynamic parameters, right? So this is clearly indicating us that enthalpy is the function of entropy, pressure, and number of particles. Now if we take number of particles as a constant like a closed system, then this is going to be zero because there is no change in number of particles, right? So this quantity is going to be absent in our case, and this is the final expression we are having if there is absence of change in number of particles, right? So this is the second important thermodynamic parameters or thermodynamic potentials which we need to know in order to know the thermodynamic parameters, right? In order to know the thermodynamic and statistical systems. Now, similarly, similarly, third one is the Helmholtz free energy. And for simplicity, we can write we can take its designation of F because someone writes free energy, Helmholtz free energy F, or some people writes Helmholtz free energy for A. So do not get confused. Both of these variables are the same until and unless it represents the Helmholtz free energy, right? If there is no notification beforehand, then you can have doubt on it, but because while writing anything with the symbol, you will be already get to know that this F represents free energy or A represents Helmholtz free energy. So the definition is, again, it is the internal energy minus temperature and entropy, right? So this is the definition of Helmholtz free energy, or U minus Ts. U minus Ts. So U is the internal energy, and difference there is minus, and time and entropy. This is the definition of Helmholtz free energy. And this is the third important thermodynamic potential which you have to know in order to know the statistical physics and other thermodynamic parameters. And the fourth one is the Gibbs free energy. This Gibbs free energy is represented by generally G, and this the definition is, it can be defined in two ways, right? So this is enthalpy minus Ts. Enthalpy minus Ts means similar to this one. This is the internal energy and minus Ts, and for the Gibbs free energy, U will be replaced by the enthalpy, right? H minus Ts. Or you can write in terms of in relation to or similar with that enthalpy as well. For that case, instead of U, we have to use the free energy. You have to use the free energy F, this one, right? So you have to use this F if you want to write in terms of pressure and volume. Or if you want to write, uh, U minus Ts, if you want to write in the form of U minus Ts similar pattern, then this is the thing you have to take into consideration, right? H is going to be equal to this one. So either way it works, right? There is no difference. Now these four thermodynamic parameters have the same format, that there is only one change in variable when you go from one to another. In this case, internal energy and enthalpy, these are looking similar, but there is the only change in the volume and the pressure. In enthalpy there is the pressure, but in internal energy there is the volume, right? And Sn they are the constant. Similar with the case of 3 and 2, there will be only change in one variable. So T V N, and in this case, sorry, it must be TP, right? So this must be TP. Oh, why is it not writing? Let me write something. So this must be TP. So this is the function of TVN, and this is the function of TPN. Gibbs free energy, the TPN. How do you know this is the function of temperature, pressure, and number of particles? The first thing is to the differential coefficient of Z, as we did in a previous class. Now we can do in this case also. So let me tell you. Let me show you. Dz is, you can take either equation. So ds minus t ds minus s dt. We are using product rule in this case, right? And ds, now again you have to go into the differential coefficient of it. The differential coefficient of h is, the h will be, for this it will be du plus pdv plus pdv, and rest remains same, tds minus s dt, right? So these are remaining the same. Now you have to replace u with the the differential coefficient of u with respect to this equation. I'm i'm neglecting this change in internal energy with respect to change in the number of particles. So it will be TdS minus PdV, or you can write, if you do not want to neglect internal change in energy with respect to number of particles, then this should be the sum, and other things remain the same, right? So PdV remains as it is, plus PdP minus TdS, finally minus SdT. So now if you simplify this one, this TdS is going to cancel with minus TdS, right? So minus PdV is going to cancel with plus PdV. Now you will be clearly known in this expression that is a function of pressure, temperature, and number of particles, right? So we conclude that Gibbs free energy or Gibbs potential is the function of temperature, pressure, and number of particles. Helmholtz free energy is the function of temperature, volume, and number of particles. And internal energy is the function of uh, entropy, volume, and number of particles. And enthalpy is the function of entropy, pressure, and number of particles. Now, how do we get the thermodynamic parameters? Let me show you. So let me clear this one, the unknown things, right? So I'm just rewriting this one, PdP minus STT, and this one plus mu T1. So now this is going to equal to dz, right? That is differential coefficient of Gibbs free energy, dz, right? Now if you want to know so you have been given that, difference, you have been given different you have been given Gibbs free energy. Now now the question is asking that get the volume, or get the entropy, or get the potential, chemical potential. Then you can clearly get the information from this differential coefficient, right? If you have been given this Gibbs free energy, then you must know how to calculate the volume, pressure, or the thermodynamic parameters like volume, entropy, or thermodynamic potential from the given equation, right? For that case, write the given free energy, given thermodynamic potential in terms of the differential coefficient, this one, like this, right? Differential coefficient. Now, if the question is asking you find the volume from this one, V is equal to what? Now, for that case, take the differential partial derivative with respect to this P, right? Because this is the B is the coefficient of differential coefficient P, right? So get this one with respect to P, and in order to get P, you have to take the differential partial derivative with respect to pressure P. Provided that you have to take this partial derivative with respect to constant T, temperature, and number of particles. Because if you take the partial derivative of this free energy with respect to pressure in terms of temperature and pressure, this is going to zero, right? And this is going to zero because both of these parameters are constant. Then only remaining variables with this one, the term that will be left out will be B, dP, and dz with respect to dp at constant t, and n will be equal to B, right? So now I think you got the basic information, right? So if you know one of these thermodynamic potential, then you can clearly get other parameters. Like in this case I have got P, right? Now if you want to know the pressure, then just you need to know, you need to take is the partial derivative of dz with respect to what? So if you want to take the, okay, this one is no, and if you want to take the entropy, then partial derivative of T, because from this equation you cannot get the pressure, because the pressure is changing in this case, so you cannot get the pressure from this differential coefficient of Z. You have to use other equation, because Z can be uh, uh, converted into Helmholtz free energy or enthalpy or internal energy. Based on these four thermodynamics, you can interchange one to another, and from that case you can get pressure or something like that. So uh, at constant pressure, partial derivative of with respect to temperature at constant pressure and constant number of particles will give you the entropy, that is with negative sign, right? So in this way you can get the information, or you can get any thermodynamic variables from the given thermodynamic potentials. That's why this is very important, right? Now let me go into the basic part. So instead of knowing the differential coefficient of these uh, internal energy, enthalpy, and Helmholtz or Gibbs free energy, you can clearly get the corresponding thermodynamic parameters. Uh, and let me show you how do you get this one. And for that case, let me erase this one. Oh, I should not have erased this one. Can I get? Let me erase this one, right? Okay. Now you have to remember this one. S U V A T. This one. And I'll tell you the mnemonic how to remember this one as well. Right? Get an arrow line drawing from S to S T, and similar get arrow line from P to P. Right? Now, four things are the thermodynamic parameters. This U, internal energy, and this A, because in this case A is suitable for this in order to make the mnemonic, so I have written A instead of F. And this one is the thermodynamic potential, and this one is also the thermodynamic potential, or you can take it as the thermodynamic square, right? You can take, and you can clearly find in a book like Carson Wang as well. So you in this case, because for a general case we are not changing the number of particles, that's why the function of the internal energy is the function of entropy and volume, enthalpy the function of entropy and pressure, and Helmholtz free energy, that is the function of temperature and volume only, and Gibbs free energy, which is the function of temperature and pressure only. Remember, these four parameters are used interchangeably, and among them these two free energies are very useful in order to know the equilibrium state of the thermodynamic system, right? Now this internal energy is being flanked by two variables, volume and S, and these are none other than the function of internal energy itself. So if you look at the function of value of internal energy, this is S and P, right? U is S and P. And if you look at the free energy, almost free energy, or simply free energy, it is the function of V and T, right? So if you look at the expression, it is the function of V and T, provided that n is constant, right? This G stands for Gibbs free energy or Gibbs potential. It is the function of temperature and pressure, right? It is the function of temperature and pressure. And in this case, this as enthalpy is the function of entropy and pressure, right? So the main thermodynamic potentials are being flanked with two functional values which these potentials depend upon, right? Now, how do you get the desired parameters? Now, if you want to get the temperature when internal energy is given, then you go like this. Take the initial partial derivative of U, and this entropy is going towards T, right? So take ds du in partial derivative of internal energy with respect to entropy, provided this P must remain constant, because you can write n also, because in this case we have taken n as a constant parameter that must be give T positivity, right? And remember one thing, so this is the thermodynamic square, right? Because this U A Z as thermodynamic potentials, and they are being flanked on each side by their corresponding variables or corresponding functions. And if you go along the arrow, it will be positive sign. So in this case, we are going along t, right? So it is positive, positive t, positive t. If you go against this t, then it would be negative. So let me go into this one, a. Now let me take this one, right, b. So this one, du, change in internal energy, partial derivative of v, partial derivative of p, and it is going towards p but against the arrow, right, against the arrows. So it must be negative with respect to provided as entropy and n. You can leave n as constant because we are not taking the change of n as a variable, so that's why it must be taken negative. If you are going along the arrow, it is taken as positive. In this case, we are going along the arrow, so it is taken positive t. But now in this case, we are going against the arrow because arrow is going from p to b, but we are moving from b to p, that's why it is negative of p, right? So these are the factors. This is the thermodynamic square, in which from a given potential, given thermodynamic potential, you can get the corresponding pressure, temperature, volume, or entropy in the case. Now you may be confused whether it is true, whether this mnemonic can be true or not. uh, you may be confused, right? So let's go into the parameter. We have internal energy over here, right? We have this, oh, we have internal energy here. That's why internal energy. Now if I take internal energy partial derivative, because I want to get t, right, temperature, what should I do? I have to take the partial derivative with respect to the entropy, ds. And in this case, what should I do? I should, oh sorry, one parameter is changing, right? P is, p must be constant as well as n must be constant. So it is going to be equal to t, right? T. Now if I need to get this p pressure, then what should I have to do? I should do partial derivative of u with respect to v, right? And so while doing this, sorry, while doing this, while doing this, what should be my constant parameters? One is entropy and another is number of particles. Entropy and number of particles, and that is going to equal to give me negative of E, right? Now look, they are equal to each other, right? They are working. Now look, these two are equal to each other. These two are equal to each other. And I already showed you these two things are this, the two things within black marker is obtained from this one, right? Exact differential coefficient of internal energy. But these two things, one blue and one green, are obtained from the third energy score, right? So it works. Isn't it amazing? Yes, amazing indeed, right? So this is one is the important thing you need to remember. Even though you are not knowing these things, but with this you can get the any parameters, any thermodynamic parameters easily. And let me go into the mnemonic part, right? How do you remember this thermodynamic square? I have made a mnemonic. So let me go into the mnemonic. The mnemonic. So this one is the mnemonic. So this one is the mnemonic I'm talking about, right? So thermodynamic square can be remembered in a sentence like this. Subodh ko car ko phone acho, right? This one is the mnemonic in order to remain the thermodynamic square. M-E-M-M-N-E, mnemonic, right? This one is the mnemonic you have to remember. And SUVAT, this is the same. This one is going from this side to this side, right? So SUVAT, Subodh ko, and Gharko with G stands for G, gross potential. Phone with letter P stands for pressure. And finally, H stands for H, right? सुबोधको घरको फोन यहाँ छु. If you remember this statement, and if you remember this pattern, because from research it is concluded that, or from the research it is observed that the figure or visual picture remains for longer bit of duration than the words one. That's why now if you go from this picture in clockwise, right, in clockwise direction, and if you remember the arrow going from S to T and P to V, and if you remember these things, then you will be knowing the all parameters from the given potentials. You can get entropy, volume, temperature, pressure, all the things from given thermodynamic potentials. Internal energy U, free energy A, Gibbs potential energy or free energy G, and enthalpy S, right? So this is the mnemonic which I am going, which I have taken from very more than years back, and it has become very easy to understand the thermodynamic variables to me, right? And I think you will also feel easy while dealing with this one. Now let's go into the second part, that is the deduction of Maxwell's identity with respect to this one, right? So let's go into the second part. Yeah, in order to get thermodynamic potentials, you already know the easy part and differential form as well, all the things, right? Now let's go into the derivation of Maxwell's identity. And these are the methods you need to know in order to have Maxwell's identity in shorthand. These are the things you need to know, right? Right. If you remember these things, then it will be easy. For before going into these methods, let's go into the thermodynamic parameters, how to get Maxwell's identity. Now if I take, as I already told you, if I take partial derivative of with respect to entropy, then what I am getting at constant V, sorry, constant V, I'm not taking this number, right? I'm not taking this one. And if I take, this will be T. And if I take partial derivative of U with respect to V, what I'm getting is at constant entropy, right? What I am getting is minus P. Get it, right? So if I take partial derivative of internal energy with respect to entropy at constant V and this number N, in this case, I'm not taking this number as a changing variable. So let me erase this one. Or you can take as well, right? So you can take number as a changing variable also. For simplicity, I'm just ignoring the number of particles as a variable. So changing internal energy with respect to entropy gives you the temperature, but you have to take it at at a constant volume. Changing internal energy with respect to volume gives you the negative pressure, but it should be taken at constant entropy, right? So now if I go on the second procedure, now if I go further in the second part, now let me take the second derivative of this one. But with respect to the change of variables, in this case I have taken the constant variable as volume, right? And in this case I'm taking entropy as constant entropy, taking change of entropy, change of internal energy with respect to volume as constant entropy, right? Now I'm going to, now if I take second derivative with respect to volume, right, it would be like this: d 2 u and d v d s, because it is like this. First of all, I'm taking the entropy second derivative with respect to volume, right, of this case. So this was the first case, change of internal energy with respect to change of entropy at constant parameters, right? Now I'm taking the second derivative with respect to change in volume, and this would give you me this expression, that is going to be equal to dt, right? Dt with respect to dv, provided this variables, this differential coefficient is taken at constant what, entropy. This is for volume, and this as a whole for entropy, right? You got me? Now in the second case, right, In this case, again, take the second derivative. Similarly, with respect to entropy, because we have already taken the derivative of intensity with respect to volume. Now, with respect to entropy, it will be like this: d2v, first of all, entropy, and then volume, right? That is going to give us negative of change in pressure with respect to entropy at what constant volume, right? Now we get this one. As you know that these thermodynamic potentials are exact, right? Or perfect differential equation. What does it mean, perfect or exact differential? It means we can get perfect differential like this one. So if these two things are if these things are perfect differential equations, right? So if du is perfect differential equation, or u is perfect differential equation, then we can get expression like this one. And you can get the definition of exact differential equation or perfect differential equation in any book related to the differential equation, right? So the requirement for differential equation to be perfect or not perfect, or to be exact or not exact, is given by this one. Let me write this one: m dx plus n dy is equal to 0. If I have this differential equation, this equation is said to be perfect. Let me erase this one. I think I do not need this one. If I need, I would get it again, right? So if this equation is the perfect, so any differential equation in the form of this one, m dx plus n dy is equal to 0, is perfect differential equation if I can get a variable like this one. Let's say I, or something like that, I xy, which is the function of xy, right, in the form of this one, m dx plus n dy, right? Or I can write this one, this differential form, I, right? So if any differential equation in the form of a form is equal to 0, now if I get this differential equation in the form of this one, better would be write differential coefficient of IA, right? If I get this form, then I should say, or the one anybody can say that this equation, differential equation, is exact, or it can be differentiated perfectly. This is the definition of exact differential equation. And sufficient condition, uh, for sufficient condition to hold whether the given equation is exact or not, uh, we must the differential equation must satisfy this condition. Let me show you the condition, and let me erase this one, right? So if I take the partial derivative of m, that is the coefficient of dx with respect to y of another variable, and that is going to equal to the partial derivative of n with the coefficient of y. And if I take partial derivative of n with respect to x, right, if I find both of them are equal to each other, so m is the coefficient of x dx, and n is the n is the coefficient of dy. Now if I take differential coefficient with respect to other variable, so m with respect to dy and n with respect to dx, and if they are equal to each other, then this condition, if this differential condition satisfies this condition, then the equation is said to be differential, exact exact differential equation, right? Or perfect differential equation. It means I can write this equation in the form of di, which is exact, or I can integrate something like that. So this one, all these thermodynamic potential are exact or perfect differential equation. So the order does not matter. In this case, d2v with respect to dv and ds. In this case, in the second equation, it is d2v with respect to ds and dv. Both of them are equal to each other. So other for the exact differential equation, the order does not matter to each other. So they are equal to each other. So if they are equal to each other, then obviously d2 by dvs with constant v is equal to the dt is equal to the minus dp, right? For a perfect differential equation, the second order derivative, because I already told you that, I already showed you for perfect differential equation, this must be equal to each other, right? d2b dv as dv by ds, right? This must be equal to each other. I already gave you the example, and this must be equal to d2b ds by dv, right? Now because they are equal to each other, they must be equal to each other. So finally I have this equation, d2 with dv at constant s is equal to minus dp ds with respect to p. All right, this is the equation we got. Now if you look at this differential coefficient, and we know that differential equation of this internal energy is exact. So what does it mean exact? What does this exact mean? I already gave you the example. If I take the derivative of this t with respect to p, that is dt dv with respect to constant s, that must be equal to the derivative with respect derivative of p negative of p taken with respect to s. That is the definition of exact, or that is the condition required for the exact differential coefficient or perfect differential equation, right? So these two things are going to equal each other. Or this is similar to say that this second derivative of internal energy with respect to pressure and with respect to volume and entropy are equal to each other, right? So this is the final case I am obtaining, right? So this is the final case I am obtaining, and this is the thermodynamics or Maxwell's identity, and this is the first Maxwell's identity, right? So in order to get Maxwell's identity, what should you have to know? You have to know the differential coefficient of the corresponding thermodynamic potential, right? So this gives you the one thermodynamic Maxwell's identity. This one gives you the second Maxwell's identity, and third free energy gives you the third Maxwell identity, and fourth thermodynamic potential gives you the fourth Maxwell identity. So from four important thermodynamic potentials, you will be getting four important Maxwell's identity, and which are very useful in handling the things, like in solving the parameters related to the Maxwell's statistical physics or heat and thermodynamics, right? Now let me go into the procedure what I have done in order to get this one. In order in Even though I'm not going to second order differential coefficient, I'll be getting directly this one if I know the differential coefficient. Now okay, let's go into the procedure. Write the differential form of potential. This is the first procedure you have to follow, right? So I'm writing the differential form of perfect differential form of first internal energy, right? First thermodynamic potential, and take a derivative of coefficient of each differential variable with respect to another variable. Now this is the differential coefficient, this is the second differential coefficient, and this is the first coefficient related to the first differential coefficient, and this p minus p is the second coefficient with respect to the second differential coefficient, right? In the second procedure, what does it say? It says that I have to take the derivative of this first coefficient with respect to the second differential coefficient, right? With respect to another way, that is dv. So differential coefficient with respect to v. And remember, the derivative is taken constant with respect to the same differential coefficient whose coefficient is taken, right? So I have taken this t for the whose coefficient is for ds, right? So it must be taken constant as. I have taken first coefficient with respect to second differential coefficient, that is I have taken derivative with respect to second variable, that is dv, provided the constant must be taken this s, that is the first differential coefficient must be taken as a constant parameter, that must be equal to the minus p. Again the same procedure repeats to each other. So this must be equal to the derivative of s, right? So this second coefficient must be taken derivative with respect to the first variable, that is ds, but provided, remember, the constant must be taken with respect to the same variable, that is dV. So V is the constant over it. And if we equal to each other, then we'll be getting Maxwell's identity, right? So these are the parameters you need to follow in order to get the Maxwell's identity. Similar for enthalpy, get the differential coefficient and follow the second procedure and equate them. For the third, get the differential coefficient, again get the derivative of one with respect to another variable and equate to each other. Then you will be the third. Similarly, you will get the fourth, right? So these are the important thermodynamic parameters in order to have Maxwell's identity, right? Now let's go into the other part, why I am stressing these things, even though you look it is simple, or some of you feel difficult. Let's go into the important other parameters, why I am considering this as the core part of this statistical physics or heat and thermodynamics chapter, right? So let's go into the important parameters, right? So let's go into the heat capacity, right? So heat capacity dq, if you go into the elementary course, dq, that is heat supplied, is equal to cv times dt, right? We are talking about heat capacity. That's why this is the definition of heat capacity, right? In this case, I'm taking n as one more. Actually, it has to be like this: ncv dt, and in this case I'm taking n as a 1, right? Because I'm going to get specific heat capacity at constant volume or heat capacity at constant volume. So heat capacity at constant volume, cv, is going to equal to dq divided by t, right? dt. Now, as we know, we already know that dq can also be written this way. So t ds, let me get into the partial derivative, because as I already told you that this s is the function of three parameters, right? So in this case, volume is taken constant. See, because at heat capacity at constant volume, in this case, the term itself speaks that it is taken at constant volume, right? So volume is taken constant. So uh, uh, in S, we are taking derivative of S with respect to T, but volume is taken constant, right? Other things may vary. Similarly, with pressure, specific capacity or heat capacity at constant pressure, it is similarly equal to dq. Similar, it has similar equation: dq is equal to cp dt times n is 1 in this case, or it can be avoided as well. So cp is going to equal to similar equation, t ds divided by dt, right? But is taken at constant pressure. So now I think you are in crucial phase, that why we are stressing the farmer topic, right? Because if I know the change entropy with respect to the temperature, or if I take the derivative of entropy with respect to the temperature and multiplied with the temperature, I'll be getting at constant volume V. Provided if I have taken at constant volume V, but instead of volume V, if I had differentiated entropy with respect to temperature at constant V, then it would be giving us, it would be giving to us that it is at specific capacity at constant pressure, right? So that's why it is very, very important. Now we can go similar expressions for other parameters also. Let's go into the adiabatic, sorry, isobaric, because the expansion is taken at a constant pressure, right? Constant pressure. So we know change in volume from elementary school, dv is equal to expansivity coefficient, original volume, and change in temperature, right? And remember, this has been taken at constant pressure. This has been taken at constant pressure at p constant, right? Now, if I simplify for this expansivity, that is alpha, or you can write gamma as well. Gamma is the expansive coefficient for volume, right? Generally in linear in a lower school or high school, we take alpha as the linear expansivity, but we are taking volume in this case. We can get gamma. We can write gamma also, because generally we write gamma for expansivity, volume expansion coefficient, right? Gamma. Or we know the relationship between alpha, gamma, and beta, superficial expansivity as well. So there is no doubt you can write either way. But in this case, I am talking about volume expansivity. So alpha is the volume expansivity, right? So it is going to be equal to 1 divided by V, and dV with respect to change in temperature, right? But provided what is constant in this case? Pressure is constant in this case, right? So this is the volume expansivity at or isobaric or isobaric. Isobar means same, iso means same, bar means related to pressure. So this is related to isobaric expansivity, because we are talking about gas in this case. So there is no linear expansion, there is no superficial or aerial expansion, there is only expansion in case of volume generally. That's why we are talking about volume expansivity, or that's why we have this expression isobaric expansivity, right? Now similar we can deal with the that's why this is very important. The relationship, the change of one quantity with respect to another constant pattern is very related or very important in case of statistical physics or heat and thermodynamics part, right? So let's go into the compressibility as well, right? Let me read this one. Compressibility, and that is, and generally this glass is fluid, so we are talking about glass in thermodynamics, heat and thermodynamics or statistical physics. That's why we are talking about volume change, and you need to worry about linear expansion or aerial expansion, because gas do not usually gas does not have such property. Gas has a volume. That's why we are talking about uh, expansivity, right? So we know from elasticity chapter, we know from elasticity chapter that bulk modulus k is equal to going to be equal to stress, right? So stress is this one. Stress is analogically, or stress is equal to pressure, but they have some different meanings. So they have some differences, but they are equal to each other. Yeah, with some differences between them. Stress and pressure have some differences between them, but they are equal to each other, right? So dp is equal, this is stress over strain. This is the bulk modulus of velocity, dv by v. Change in volume with volume. And remember, this is taken at, this is considered for at constant, t is constant. It means temperature is constant in this case while we defining this one. All right, temperature constant. So bulk modulus is equal to the negative of change in stress, or stress over strain. Stress is equal to pressure as well. That's why with some differences you have to keep it in mind. And this is the change in volume over original volume is the strain, right? So this is the definition of bulk modulus of elasticity. And also we know bulk modulus and compressibility c, or you can write kappa t as well. That is going to equal to each other with reciprocal to each other. It is the definition, right? 1 by k. And you may be surprised why there is negative p, because in case of gas, if I increase the pressure, now if this is the system containing the gas, if I increase the pressure from all direction, then this volume is going to decrease, right? So it is going to in a lesser size, right? To a lesser size. That's why there is negative sign over there. You got me, I think. You got me, right? Generally they have opposite signs. And you can talk about expansion as well. Yeah, you can talk about expansion as well. But in in case of gas, we are talking about, generally we talk about compressibility because we are dealing with compressibility. That's why we are not talking about expansivity, because the expansivity is already talked about in isobaric expansivity. That's why we are not talking about expansion. We are talking about compression. That's why there is always negative sign, right? For compression, but for expansion there can be positive sign as well. So this is the relationship. And if you write for 1 over k as this one, then this one is going to 1 over k is going to be equal to v with negative sign, right? Is it negative or not? 1 by k. So sorry, let me go into the detail part. So 1 over k is going to equal to dphi, right, over expansivity. So if I write this equation, it will be like this: dp over dv, again divided by p, because this is large expressions. It is looking like awkward like. So finally it will give you minus change in volume with respect to pressure, but remember the temperature is taken constant and multiplied with 1 over v, right? Now you can get it in simple form as well. First convert this into simple form, that is, if you want it in simple form, dv times, now you have to reverse the order, right? If there is in fraction denominator like this, dv, oh sorry, v over dv, right? Now dp and v are in the same order, so dp and v is in the same multiplication part, right? And dv is in the denominator. When you take either, when I take the reverse order, then it goes into the numerator side. So this is the relationship for isothermal compressibility. So this is for isothermal compressibility. Isothermal compressibility, compressibility. So that's why these are very important relationship in order you have to know. And for this, you for these important parameters to know, you must know 4 important thermodynamic potentials and methods to know the Maxwell identity. I think you liked this video. Next time I will be uploading the new video. Thank you very much. And namaste. Take care yourself. Thank you very much.